Hello, welcome to Algebra 1 with Miss Andrea. Today we are going to continue looking at some, we're starting a new unit, first of all, but what we're going over is still about functions, and we're going to look at some characteristics of some functions. Getting into our unit is called comparing and contrasting functions. Now, this is module 7. However, I believe it's called unit 5 in the online book if you're following along online. And this is page 1 in the online book. So we're going to call it lesson 1. Algebra 1, comparing and contrasting functions, lesson 1. Here we go. Remember, lesson 1 is all about keywords. So our first word is an arithmetic sequence. So what is an arithmetic sequence? We've already discussed that in a previous one, but it bears repeating. An arithmetic sequence is something like 1, 2, 3, 4, 5, and so on. If you notice, the difference between each of these is exactly the same. It's 1. Okay, here's another type of arithmetic sequence. 3, 5, 7, 9, and so on. The difference between 3 and 5 is 2. 5 and 7 is 2. 7 and 9 is 2. So it's a sequence of numbers in which the difference between any two consecutive terms is going to be the same. Now, it can be any number. It can be 100, the difference between them. So you could have 200, 300, 400, etc. Because the difference between those is what? 100, right? Between consecutive, meaning in order, numbers. Consecutive, 200 and 300 are consecutive because one comes right after the other. Okay, and the difference between those is 100. The difference between these is 100. The difference, how you find the difference is A minus B. It's the absolute value of it. So it doesn't matter what order it's in. You could do 200 minus 300. That's going to be negative 100, but remember, we're finding the absolute value. Or you could do 300 minus 200, absolute value. Whenever you find the difference, it's always absolute value. All right. Our next key term is the average rate of change. Now remember that rate of change is going to be, if you have 2 points, is going to be the difference in y over the difference in x. Okay, so the average rate of change is the change in value for a function, y value divided by the change in the x value. So this formula right here. Remember, change in y divided by change in x means y1 minus y2 over, x1 minus x2. So if you have a point, you're going to have x1, this is 0.1, x1 and y1, and you're going to have 0.2, and it's going to be x2 and y2. So you're going to plug them into this formula to figure out what the average rate of change is. And if this rate of change, another way to call it is going to be a slope, and we identify that with an m. And then for items such as a parabola, your rate of change average rate of change will change depending on what 2 points you take. However, if you're doing a straight line, no matter if you take the 2 furthest away points or 2 closest points, any 2 points, it's going to be the same. This is called a constant rate of change. This rate of change varies, it's dependent on the points that you chose or are given. All right. So, that brings us to our next question, constant rate of change. So that's essentially what we just talked about. If you have a straight line, you will have a constant rate of change. If you're given a rate of change of a function instead of looking at a graph and you see that the rate of change is constant or always the same number, then you know it's going to be a line. So continuous is, it's a set of numbers or such as an interval. So 1, 2, 3, 4, 5. They're connected. If you talk about it in a graph, it's just going to be whatever graph that's connected. Whereas I don't know if it's the next one. Hopefully it is. Discrete. Nope. Discrete. Oh, there it is. It is the next one. Discrete is going to be separate. So you'll have dots or even lines that are separated and not touching. And so you'd have like 2, 7, 12. Okay, they're not touching. They're not continuous. So discrete functions and continuous functions. Domain. Domain is the set of the x coordinates that are possible with a graph. Okay, so let's talk about a few graphs here. The three main type of graphs that we will get into. The first one is that I want to talk about is the quadratic, which is what we just recently went over. That's a parabola that you see there. And the domain is all real numbers, right? And that's represented by a negative infinity to a positive infinity. That's another way to say that for the range, right? X is, okay. So then another type of function we had was, whoops, I did not draw that very well. What type of function was that called? Do y'all remember? This was called exponential. Okay, and the range was all real numbers again. Oh, excuse me, I said the range. I don't know if I said that for the last one too, but we're on domain. Domain, that's all the x values. So any possible x value. Domain is any possible x value. How many things could it be in x's? Is there a limit to the x's that it could be? Okay, and then also we've got a linear function, right? And this linear function will have a domain of all real numbers, which again, all of these can be written in that same format, the set notation format of parentheses, negative infinity to positive infinity, because all of these have the ability to have any x value at all, ever. So it's domain. End behavior. So the appearance of a graph as it is followed further and further in either direction. End behavior of this graph as x is approaching infinity. So as the graph is going in this direction, as x is going this way, what's happening to y? Y is what? It's approaching what? It's going upwards, right? It's approaching infinity. Now, if it had a stopping point, it would be approaching that stopping point and not infinity, but it's going on and on forever in that direction. What if x were going the other way? What if x were approaching negative infinity? So as x goes to the left, what's happening to y? Well, y is getting lower and lower and lower. So, but there's something it can never touch, right? With this type of a graph, it can never go past a certain line. And for our general, our standard exponential equation, that's going to be 0 or the x-axis. So it's going to be approaching 0. And behavior of a line, you could have a line. Let's do a line that goes the other way. You could have a line like this. And you could say as x is approaching infinity, what's happening to y? So as you're moving this way on the graph, what way is y going? Y is approaching negative infinity. And as x is approaching to the left, that's negative infinity. What's happening to y? Y is doing what? It's moving upwards. So it's approaching positive infinity. So that's end behaviors. You need to be able to identify end behaviors. Explicit expression. Remember when we got into sequences, we created two types of expressions or equations to help us determine what a term was in that expression. So an explicit expression allows us to write a formula in which we can say, oh, I'm looking for the 12th term in this sequence, and you plug in the number 12 because that's what you're looking for, and the explicit expression will spit out the correct answer for you. And you don't have to choose 12. I just chose that number. It's what we call the nth term, meaning whichever term you want, you can plug into that formula and it'll shoot out an answer for you. And so that's an explicit equation. Exponential function, we already discussed those. You can either have exponential growth or you can have exponential decay. Okay, we're going to get into some of the features of these in a future lesson. Exponential model, it's going to be an exponential function representing real world phenomenon, aka a word problem in which you use an exponential function. Okay. Even functions. These are going to be functions that are symmetric with respect to the y-axis. And we're going to get into this in the very next lesson. But remember, you have a y-axis here and an x-axis here. If you have something that, let's say, a straight horizontal line, if you were to fold this in half along the y-axis, this would be symmetrical because they would fold directly on top of each other. However, if you were to have a diagonal line, that would not be symmetrical to the y-axis because it would not lay on top of the other one. It would look up here. So an even function has symmetry around the y-axis. A factor for any number x, the numbers that can be evenly divided into x are factors of x. Okay, so what does that mean? All right, so what are some factors of 20? Well, some factors of 20 are, okay, well, there's 1 times 20, 2 times 10, 3, 4 times 5, and then if I choose 5, I'll be back again. So the factors of 20 are 1, 2, because usually you want to write them in order from least to greatest, 1, 2, 4, 5, 10, and 20. And remember, we can do this with functions as well. Oops, I didn't mean to put the parentheses around that. X squared. Let's see, let's do it this way. X squared minus 8x plus 16 can be factored out to x minus 4 squared. So x minus 4 is the only factor of x squared minus 8x plus 16. Because it repeats because it's there twice, but it's the only factor. All right, a geometric sequence. Remember, we talked about a geometric sequence. Instead of going up by the same number, they go up by a ratio. And so this is going to look like something that's multiplied or divided. So here's something that you could say 1, 3, and then 3 times. So 1 to 3, you had to multiply by 3. 3 times 3 is going to be 9. Times 3 is 27. Okay, so the ratio of each of these are going to be the same. So instead of finding the difference to determine if a sequence is geometric, we find it's a ratio. And what does that mean? How do you find a ratio? Well, you just divide. You take 27 and you divide by 9. And what does that give you? That gives you 3. So the ratio is 3. And then take 9 and divide by 3. And what do you get? Oh, it's 3 again. So the ratio for those is 3. And then you take 3 and you divide by 1, and it's 3. So the ratio there is 3. So this is a geometric sequence because the ratios are the same. Remember, if the differences are the same, it's an arithmetic sequence. Comparing and contrasting functions, horizontal shift. Okay, so if you have a parabola, a horizontal shift would be to take that exact same parabola and shift it over however many spaces to the right or to the left. It looks exactly the same. I know I don't do the greatest job of drawing it exactly the same, but I try to get close. All you're doing is taking it and moving it to the right or to the left, not doing any other changes when you're referring to a horizontal shift. Now you can change things in multiple ways, but specifically a horizontal shift is just talking about the movement to the right or to the left. I think that sometimes they call it a transformation to the right or a transformation to the left. Interval notation, that is, like we said, x is less than 10. You could write that in interval notation as x is an element of negative infinity to 10. So it can go anywhere from negative infinity all the way up to, but not including, because of the parentheses, is 10. If you said x is less than or equal to 10, you would say x is an element of negative infinity to 10 with a bracket, because this is telling us that x can go anywhere from negative infinity all the way to and including 10. Linear function. A linear function is a function in which the graph is going to look like a line. Okay, it's got a constant rate of change. Those are the two key features you need to know about a function and whether or not it's linear. We're going to get into some more of that in a future lesson, but it looks like a line and it's got a constant rate of change. Those are some key ways to identify those. Linear model. Again, just like with the exponential model, it just means applying what you know about linear functions to real life situations, aka word problems. Odd function. Okay, so we talked about an even function was able to be flipped and symmetrical across the x-axis. Well, when it is what we call an odd function, it has what we call about the origin symmetry. And that means that if you take, it's basically symmetrical on a diagonal. And so how you get there is you flip it across the x and the y. And then if it's symmetrical that way, then you can tell that it's an odd function. So here is a graph. And if we were to flip that across the x-axis, it would look like this. Oops, I used the same color accidentally. And then if we flip that across the y-axis, it's going to look exactly the same as the red. So it did not end up back as the black one. So this is not an odd function. So what kind of function, Miss Andrea, is an odd function? Well, I'm so glad you asked. It's going to be something that definitely goes through the point of origin here. Oops. Straight down. Straight up. So this is an example of an about the origin or odd function. So if we flipped it across this x-axis right here, it's going to look like this. And then if we flipped it again across this y-axis, this is going to come over here and go like that. And this yellow is going to come over here and go like that. And so we ended where we started. And so this is an odd function. When it flips across both the x and the y-axis, do each of those and still end up exactly where you started. That is considered an odd function. And here's some additional details that we might get to a little later. Parameter is the independent variable or variables in a system of equations with more than one dependent variable. So if you have y equals x plus b, so you've got two variables, x and b. Okay, so it's going to have, usually you're going to have a system of equations with x, y, and z. You're going to have to add them and subtract them and things like that. Quadratic equation, that's what we just finished, so it should be fresh in your mind. Remember, it's going to look like a parabola. It has a second degree, meaning y equals, ax squared plus bx plus c. This right here tells us it's a second degree. What was a linear function? It It was the first degree, right? Y equals mx plus b. There is nothing here, which means there's a 1 there. So it's a first degree, okay? And it has at most 2 solutions, because if it crosses the x-axis, it could possibly cross it up to 2 times. So it has at most 2 solutions, could have 0 or 1 as well. All right, a quadratic function isn't that what we just did? Oh, we did an equation. Okay, so a quadratic function just is specifically a function that's either going to go open straight up or it's going to open straight down. It's not going to open sideways. So you get into these sideways ones when it's something like y squared equals x plus 3. So when y is squared, it looks like this. When x is squared, it's going to look like this. If you have something like xy squared equals, it's going to look diagonal. Just so you know, the more you know, the more fun you have in math, right? So this is the only one that counts as a function because it passes the straight line test, right? That's an easy way to check for functions if you can see a graph. If you can't see a graph, you need to actually know what a function is, which means for every one input, there's exactly and only one output. So you can't have multiple outputs for a single input. You can't put milk and sugar and butter in a pan and stick it in the oven and get both cookies and cake. You can only get one thing out every time, no matter what. All right, root. So that's just another word for the solution, whether usually it's used with a parabola or a quadratic equation, but the root is going to be also known as the zeros or the solutions. It's where the graph is going to cross the x-axis, okay, and is the x value. So it's going to be x, whatever that x is, because y will always be 0. It's going to be whatever that number is. That's going to be the root, the 0, or the solution. All right, range. So we already talked about domain, right? Domain and range, they go hand in hand. So if domain was everything that goes across on the x-axis, range must be the opposite of that. It can all the possible y values, right? So all the possible y values. Let's look at the different types of graphs we've learned about so far. We've got a linear function here. Is there any limit to what a linear function can do? Linear. No. So the range in this case is going to be all real numbers. Well, how do we represent that as a in set notation? Well, y can go from negative infinity to positive infinity, right? What's another graph we looked at? Okay, now this one has some limits on the range. So is there something where this graph can't go any further down or further up? Oh, well, this is supposed to actually cross at the 1 point right there. But is there anywhere where it can't go below or above? Well, yes, this has a line here at the x-axis where x equals 0 that it can never touch because it's its horizontal asymptote. Remember, that means that it's getting closer and closer and closer to it, but it can never go to it. So in this case, in this exponential function, our range will be 0. It doesn't include it because it can never actually touch it, to positive infinity. Now, remember, you can always shift these graphs. You can have it look like this. And in that case, it's going to have a different number here instead of 0. You could also have it, you could have it flipped upside down and have it look like this. In that case, it would go from negative infinity. It would have a maximum instead of a minimum. So it's from negative infinity down here is all the possible y solutions up to whatever this number is. Let's say it's about 1. So you could say negative infinity to 1 is the range for that green one. Okay. What's another type of graph we looked at? A parabola. which is called what? It's not called a parabola. It's a quadratic function. And the domain for this is going to be from wherever the minimum or maximum point is to infinity on the other side. This opens upwards, and so it's going to go to positive infinity. Okay, let's say that that's right there on the 0 line, so it's 0. Now, is that 0 included? Yes, because it is on the graph. So we're going to use a bracket there instead of a parentheses. Last one, let's go here to -1 and just say we had a parabola that opens downwards. What would our range be on this one? Well, it's the lowest point it can get to is -infinity, right? The highest point it can get to is going to be -1, and that is included. So we've got the linear here is in black. Unless you have an exact horizontal line, your range for any linear equation will be all real numbers. Exponential here, we had it in red. This was an exponential growth, so it goes from the horizontal asymptote to infinity. Exponential decay goes from -infinity to the horizontal asymptote. Then with the quadratic, if you have a minimum, it goes from the minimum, which is included, to infinity. If you have a maximum, it goes from -infinity to the maximum, which again is included with the brackets. All right, recursive formula. We already talked about the other type of formula, but a recursive formula is when you have sequences, whether it's arithmetic or geometric, and the sequences, you create a formula in which you can determine an nth number in the sequence. But with recursive, you have to have you have to already know at least one of the other terms. So you have to know that the first term is this, or the second term is this, in order to determine what the term that you're looking for is. So it's kind of dependent on knowing one of those other ones. A vertical translation, just like a horizontal translation, is when you're going to move a graph. But this time, instead of moving it horizontally, we're going to move it vertically. So here's graph 1, and here's graph. Oops, I didn't do that very well, but we just took the first graph and moved it up just a little bit. That's all we did, no other changes. That's a vertical translation, or a vertical shift can also move downwards. X-intercept, that is where any graph crosses the x-axis. So whether it's a straight line, whether it's a parabola, that one doesn't have an x-intercept because I did not draw it well, or whether it is an exponential equation that has been obviously shifted and moved and transformed. Any of those, wherever they cross the x-axis, is the x-intercept. Which brings us to the last term. Well, if the x-intercept is where it crosses the x-axis, what do you think a y-intercept is? Well, that's going to be where it crosses the y-axis. So here we have a parabola. There's the y-intercept. Here we have a straight line, and there's the y-intercept. And here we have an exponential function that's supposed to actually look more like that. And here you have the y-intercept. Wherever the graph crosses the y-intercept is, or the y-axis is the y-intercept. All right, so all of these questions you should be able to answer or understand, know the answers to, know the information about by the end of this unit. And it's a short unit. I think there's only 4 or 5 lessons in it. So how do I use graphs to represent and solve real world equations and inequalities? Why is the concept of a function important? And how do I use function notation to show a variety of situations modeled by functions? How do I interpret functions that arise in applications in terms of context? How do I use different representations to analyze linear and exponential functions? How do I build a linear or exponential function that models a relationship between 2 quantities? How do I build new functions from existing functions? How can we use real-world situations to construct and compare linear and exponential models and solve problems? How do I interpret expressions for functions in terms of the situation they model? How is a relation determined to be linear, quadratic, or exponential? What are the specific features that distinguish the graphs of a linear, quadratic, and exponential function from one another? That's a lot of questions. Some of them you may already know, but any ones you don't know, you will know soon.